Welcome to Signals and System subject classes. Now we are in the fifth chapter, that is continuous time Fourier transform. So still now we finished this continuous time Fourier transform topic. So that is related to the Fourier transform formulas and properties of the Fourier terms. Everything I have finished, and also we have discussed about some problems asked in the engineering service examinations also. So this is the 8th video. So in this video, we are going to revise the whole chapter. For that, now we are going to revise the whole chapter. For that, here I'm taking the one continuous time signal. So this x of t is a continuous time signal. So before writing the formulas for the continuous time signal for a transform formulas, I would like to write formulas for the Fourier series. We know that Fourier series, continuous time Fourier series, that signal in time domain, that is denoted by the x of t. So this is Fourier series, the Fourier series coefficient. This is signal in the frequency domain. The formula for the any signal, any periodic signal can be represented in terms of the exponential complex signal, that is called Fourier series. You know very well. So here I'm writing. So some of the exponential complex exponential complex signals, complex exponential signal, anything, both are same. E power jk omega naught into t, k from minus infinite to the infinite. Then you know that Fourier series coefficient. This is discussed in the third chapter. Fourier continuation Fourier series. This is the third chapter. If you have any doubt, you go to the third chapter in our channel. So AK equal to 1 by t for the integration. We are doing the integration for within the one time period. Why? Because it is a periodic signal. We know that continuous time Fourier series is applicable for the periodic signal. X of t into e power minus jk omega naught into t into dt. So this is about Fourier series. So in case of the continuous Fourier transform, we know that signal it is also converting from time domain to frequency domain. So signal it is a signal in time domain x of denoted by x of t. So Fourier transform. So that is the Fourier transform. We know that x of j omega. This is Fourier transform. So in first of all, I would like to write formula for the Fourier transform. You know that x of j omega in the derivation, I told you this x of j omega is nothing but ak into t. Simple thing. The ak into t is nothing but x of j omega. Then it is also integration. So the x of t signal, so x of t is aperiodic. So we should take the limit from the minus infinity to plus infinity. So x of t into e power minus, here minus and here also minus, e power j. So k omega naught would be replaced by the omega. So omega into t into dt. So this is the continuous time Fourier transform formula. Then inverse Fourier transform formula, that is x of t. So that equal to 1 by 2 pi integral, so minus infinite to the plus infinite. So x of j omega into e power j omega into t into d omega. So these are the Fourier transform formulas. You know very well. So first of all, we have to finish properties of the continuous Fourier transform. Then we go for the formulas. In one table, we will write. So the properties. So in this, so properties. It's a Fourier transform. So Fourier transform is x of j omega. For the all properties, we are considering this is the reference. Linearity, you know that addition and scaling, additivity and scaling, superposition theorem. A into x of t plus b into y of t. In the Fourier transform also, we are getting same. So A into that x of t Fourier transform equal to x of j omega. So plus b into y of j omega. The second one, that is time shifting. Time shifting. So time shifting is nothing but so in the x of t minus t naught, this is delayed signal of x of t. For that, x of j omega, it is multiplied by the exponential, that equal to e power minus j into omega into t naught. For the positive, you should write plus. So this is the time shifting property. This is very, very important. So this is very, very important. Then third one also, frequency shifting. Frequency shifting property. So the frequency shifting property is nothing but now shifting in. So shifting in the frequency signal, that is see here this x of j omega minus omega naught shifted in the frequency domain. For the corresponding signal in the time domain is nothing but x of t must be multiplied by the exponential, that equal to here minus here this is we will get the plus j omega naught. Where is shifted? Omega naught shifted. So omega naught into t. This is the case, frequency shifting. So it is also a very important property. Mm. Next one, complex conjugation. So complex conjugation. In complex conjugation, so x of t complex conjugation. So in frequency domain, it is also complex conjugation, but omega must be replaced by the minus omega. That is the difference. So fifth one is time reversal. So in time reversal, see if signal is time reversal in time domain, reversal in time domain in x of t, same reversal happening in the frequency domain, that is so x of j omega, x of t Fourier transform equal x of j omega. For minus t, omega must be replaced by the minus omega. This is x of j omega. This is next sixth one, time scaling property. So this is a very, very important time scaling. So what is the time scaling? X of at. You should remember this x of at. If a less than one, a less than one, that is a stretched signal. A greater than one, that is compressed signal. This is a topic discussed in the first chapter. Here I'm not writing that information here. Already we have discussed in the why. So this is a time scaling 1 by mod a x of j omega by a. In Laplace also same property. So this time scaling also is very, very important. Should remember this is. So it's very, very important time scaling property. Next one, seventh one is convolution. In the continuous time Fourier series, it is called periodic convolution, but it is aperiodic. Then just we are calling as a convolution. Convolution. For the convolution, simple thing, the convolution we are taking in the time domain convolution, but the corresponding operation in the frequency domain, that is a multiplication. Simple convolution in time domain, the corresponding in frequency domain, that is multiplication. So just multiply the frequency domains. That's enough. X of j omega into y of j omega. It is also very, very important convolution for the analyzing the systems in continuous, in analog systems or digital systems, in control system. We can able to write easily the relation between the input and output and system transfer functions. The transfer function of the system is nothing but y of j omega by x of j omega, or y of j omega equal to x of j omega into transfer function of the any system. So this is related to the convolution. So similarly, in the multiplication in the time domain. So multiplication, now this multiplication happening in the time domain. So x of t into y of t, then so what will happen in the frequency domain? So it is simple thing. So multiplication in time domain, convolution in frequency domain, that's it. So x of j omega, so convolution into y of j omega. How to apply the convolution? Already explained in the chapter. That is, I think, video number third or fourth. I think third one. The next one, ninth property. So, so ninth property, that is differentiation. So differentiation in time domain, not in frequency domain, in time domain. We'll see what will happen. Already you know that. So differentiation in time domain, then so simple, the j omega multiplied with the x of j omega. That is the difference. Now the 10th one is, so it is also very very important. You should remember. So this is, so 10th one, integration property. Integration. So minus infinite to the t x of tau into d tau. So that equal to x of j omega divided by the j omega plus pi into del of omega into x of 0. So x of 0 is nothing but 0 substituted in the x of j omega. So this is the Fourier transform. So it is also important property. So the 11th one. Now this is differentiation in the frequency domain. Previously we have taken the differentiation in time domain. Now, so it is in the differentiation. So differentiation in the frequency domain. Sometimes it works as a line and automatically taking the line, but sometimes it is not working. I will check it. Okay, so differentiation. So in differentiation in frequency domain, so d by d omega x of j omega. This is differentiation in the frequency domain, that equal to minus j, that equal to minus j into t into x of t, but I'm taking the minus j into the frequency side. So send to the right side. So 1 by minus j, so it becomes plus j. This is the case. So j into d of d omega x of j omega is, it is a Fourier transform of the t into x of t. So it is also important property. So next one, conjugate symmetry. Already it is discussed in the conjugate symmetry in conditional Fourier series. Same thing. But in the previously we have taken, that is discussed in the terms of the AK. But here we have to discuss in the x of j omega. So for that, now this x of t is a real. So then real. So then complex conjugation also same signal we will get it. For that, so x of j omega, so x of j omega complex conjugation, it is equal to the, sorry, mm, then the complex conjugation of minus j omega, it is equal to the x of j omega. Why? Because x of t is a real. So real part of, x of j omega, so it means that x of j omega is a function of a complex variable. So complex function. So that equal to same thing. So it equal to real part of x of minus j omega. Next, imaginary part of x of j omega it is equal to minus imaginary part. Why? Because in x of minus j omega, this is, it can be written as a real part minus j into imaginary part. Real function and minus j into imaginary function. So that's why here we get a minus imaginary part of x of minus j omega. So it is about real part and imaginary part. Next, the magnitude and angle between the x of j omega and x of minus j omega. So the magnitude of x of j omega magnitude. This is, it is denote, it is used for the magnitude. So the magnitude are same. So x of minus j omega magnitude also same. But the angle is different, 180 degrees phase shift between these two. So angle of x of j omega equal to minus of, so this minus is nothing but 180 degrees difference between the x of j omega and x of minus j omega. That is the case. The next 13th one, real and even. See, real and even signals. So this x of t, it is real and even. So x of j omega also real and, until unless it is odd, it follows same. Whatever x of t real and even, then x of j also same thing. So in 14th, now this is real, but the signal is odd. So, so this x of t real but odd. Then, so x of j omega, it becomes purely imaginary. Even though we are taking the x of t is a real, but it is purely imaginary. Imaginary and same odd. So this is a real and odd. Then next, even part and odd part. Even and odd decomposition of decomposition of real signals. So even part, so you know that even part of xc of t, that is even part of x of t. So its Fourier transform equal to, very sorry. Okay, so its Fourier transform. So even part, in Fourier transform, it is equal to real part of the x of j omega. So real part of x of j omega. So odd part, it is nothing but odd part x of t. So it is a Fourier transform. So j into imaginary part, j into imaginary part, imaginary part of x of j omega. So this is the case. So last one, part-source relation. It's very, very important. In previously also, in last video also, we have done problem based on part-source relation. So this is it is a energy relation. Here, how to remember this part-source relation? This is the very, very important. Simple thing. In left side, you take the x of t time domain. In right side, x of j omega. First, write down formula for the x of t. So x of t formula that equal to 1 by 2 pi integral of minus infinite to the plus infinite. So x of j omega into e power j omega t into d omega. So this is the energy relation. So integral of power is integral of power, it gives the energy. So that's why here we should take the power. So mod of C. Then the mod of exponential, it goes to 1. Simple thing. Mod of the exponential always goes to 1 into d omega. Now write down the formula for x of j omega. X of j omega formula, simple integration. There is no multiplication. There is no factor. So minus infinite to plus infinite. So this is the energy. Energy is nothing but integral of the power. So power is nothing but square. Then the mod of the exponential, it goes to 1. Then the last term is dt. So this is the partial relation. It is for the energy of a signal, meaning the total energy is the same whether measured in the time or the frequency domain. That is the case. So next, we are going for the formulas for the aperiodic and periodic. Here I am writing in one place, in one table. This is very, very important. Try to remember. You write in one place completely. So first, we are going to write the Fourier transform for the periodic signal. In the first one, periodic. First one, periodic. For the periodic, here one column for the time domain. So one column for the Fourier transform. So it is a periodic signal. So periodic signal. So periodic signal, automatically we know that it has Fourier coefficient. So for the Fourier coefficient, also we are taking one column. So first, I am taking the general any periodic signal. We know that any periodic signal, it can be written as sigma ak into e power j into k omega naught into t. So any periodic signal, it can be represented as this equation. Now this ak, so corresponding signal that ak for all values, is it for all time? So Fourier transform, that for the corresponding Fourier transform, you know that it is also impulse train. So for the how to write the impulse train, tell you. So impulse train, so 2 pi into ak. So impulse train magnitude equal to 2 pi into ak. So del of omega minus k into omega naught. So we know that what is omega naught? Omega naught equal to 2 pi by t, capital T. So here also the k also minus infinite to plus infinite. So this is a general Fourier transform for the periodic signal. So del of omega del of t Fourier transform equal to 1, and so one is a periodic signal. So after the duality property, so del of t Fourier transform equal to 1. So after duality property 1, its Fourier transform equal to 2 pi del of omega. Is it? Now, so e power j into omega naught into t into 1. So this is 1 multiplied by j into omega naught t. So for what case we are getting this e power j omega naught t? For the frequency shifting. So, so frequency shifting. So this is multiplied by the 1 multiplied by the here 1. Here I'm assuming this is 1 multiply here, then apply the frequency shifting. So the one Fourier transform equal to 2 pi, so del of omega minus omega naught. So for the sine function, so we know that cos omega naught is nothing but e power j omega naught t plus e power minus j omega naught t by 2. So after simplification, we're getting, so pi is a common, so del of omega minus omega naught plus del of omega plus omega naught. So this is we have discussed in detail in previous videos. So okay, so what about the Fourier series coefficient? For this Fourier series coefficient, so there is no exponential, but this is called a naught value. Is it a naught? So for the a naught, e power j into 0, it goes to 1. Exponential goes to 1. So here a naught equal to 1. In this case, so this is a1. A1 here k equal to k, here k value equal to 1. So automatically this is a1 value. So a1 value equal to 1. Otherwise, all coefficient goes to 0 in this case also. So here it has a1 and a minus 1. a1 and a minus 1 both are equal to 1 by 2. Minus 1 that equal to 1 by 2. So otherwise, all Fourier coefficient goes to 0. So similarly, so sine omega naught t here also. So we will get the corresponding Fourier transform pi by j so del of omega minus omega naught minus del of omega plus omega naught. So this is corresponding Fourier transform for the sine omega naught t. So but here the a1 equal to 1 by 2j, but a minus 1 equal to minus 1 by 2j. For that case, here I am writing a1 equal to 1 by 2j, but a minus 1 equal to minus 2j. So here I am writing minus that equal to, so a1 equal to minus a minus 1 that equal to 1 by 2j. Otherwise, all coefficient goes to 0. So these are the period signal for these Fourier transforms are in second column. Last two, one is periodic rectangular pulse. So x of t, so this is periodic rectangular pulse for mod t less than t1 and t1 to the mod t up to by 2, that is 0. So this is, we have taken the values for the only one time period. For the case ak equal to 2 sine k omega naught into t1, so k omega naught into t. So this is the Fourier series coefficient. So I'm not writing this ak value in this one. So just simply I'm taking the simple formula 2 pi ak general formula. I'm not substituting ak value. Why? Because this is a bigger one. So ak. So you should write this formula in this equation. Then we will get the Fourier transform for this one. ak into del of omega minus k omega naught. Everything, all these are discussed in the previous classes. K equal to minus infinity to plus infinity. The last one, last period signal, that is impulse train, that equal to sigma del of t minus n into capital T, here n from the minus infinity to plus infinity, the time period equal to capital T. For this case, the Fourier series coefficient ak equal to 1 by t. Then substitute this 1 by t in this ak. So here I'm writing that constant 2 pi by t sigma del of omega minus k into omega naught. So what did you understand here from this formula? The impulse train, this is impulse train, it is also impulse train. So impulse train of the any signal Fourier transform is also impulse train. For the linear frequency, for example here, for example, I'm writing like this. So x of t equal to sigma n equal to minus infinite to plus infinite del of t minus small n. So here capital T equal to 1. So here I would like to write Fourier transform in the linear frequency for the case. So in linear frequency there is no 2 pi and t equal to 1. Is it? Then so directly here writing. So sigma k equal to minus infinite to the infinite. So delta f minus k into that omega naught we can write like f naught. So impulse train, its Fourier transform also similar to the same Fourier transform, but it is written in terms of the time. It is has to write in terms of frequency. So it's very fundamental concept. Then for the aperiod signal, for the aperiod signals, so only two columns, one for the x of t, another for the Fourier transform. There is no column for the AK. Why? Because it is aperiod signal. We can't write Fourier series for the aperiodic. The first signal here, this is period signal. I want to write aperiod signal for aperiodic. See, I'm writing this aperiodic signal, rectangular pulse. One for the mod t less than t1, 0 otherwise. So mod t greater than t1. After t1, there is no signal. So this is the aperiodic, this is a periodic. For that case, so ak into t is nothing but x of j omega. So 2 sine k omega naught must be replaced by the omega and t1 by, so already we sent t to the here, so k omega naught by omega. So this formula easily we can once you remember this formula, so you can easily able to write Fourier transform for the aperiodic rectangular pulse. This is the case. So properties also, whatever you studied in the Fourier series, same you can able to write properties in the for the continuation Fourier transform, also in discrete time Fourier transform. See this formula and this formula same thing. If you learn conceptually in the signal system, whether it is Fourier series or Fourier transform, you can able to remember all formulas. So then next, so this is rectangular pulse Fourier transform is a sinc function. So I'm taking the rectangular pulse in frequency domain. So that is x of j omega. So this is same 1 mod omega less than w, mod omega out of the w there is no signal. So this is the rectangular pulse in frequency domain. Same thing here also we are getting same sinc function that equal to sine wt by pi t. Already I told you it is also sinc function. We can able to convert the signal to the sinc. Then no, so the del of t Fourier transform equal to 1. We know that already here we have written. So time shifting del of t minus t naught, that equal e power minus j omega into t naught. See, okay, so e power j omega naught t, but so this is the function of t, this is the function of the omega. T naught is a constant. Next, e of t is a unit step signal. So this is Fourier transform equal to 1 by j omega plus pi into del of omega. This we can write with help of the integration property. Once, if you want to write the Fourier transform for this, first of all, you have to write u of t in terms of the impulse, then apply the integration property. Then you will get this formula. U of t, then e power minus at into u of t. So this is Fourier transform equal to a plus j omega. Now, I would like to multiply t to the above signal. So we know that once t multiplied to any signal, that is nothing but j into d by d omega of its Fourier transform. Its Fourier transform equal 1 by a plus j omega. After completion of the differentiation, we will get formula like this: 1 by a plus j omega square. For the t square we will get like e power minus at u of t, that is in numerator we will get 2 by a plus j omega to the power of 3. For the t power 3, so here again we get 3 into 2, so e power minus at into e of t, so that equal to 3 into 2 into 3 into 2 a plus j omega power of 4. So in last step, so t n minus 1. So the factorial, so this is 3 fact. So here I'm writing in left side. So n minus 1 factorial into e power minus at into e of t. So it's Fourier transform. So that equal to 1 by a plus j omega to the power of, so this is n minus 1, take n. So this n minus 1 factorial you can take here or here. Fourier transform. It's better to write these arrows. Yeah. So this is about continuous time Fourier transform. So we finished with continuous time Fourier transform. So this is in signal science system, this continuous Fourier transform. This is it's very important. I will give priority to this continuous Fourier transform among all transform. The second priority goes to the Laplace transform. Thank you.